This is your lesson on 6.1. 6.1 is the start of chapter 6, which is all about polygons, but more specifically quadrilaterals. The only section that we really deal with polygons would be section 1, and then once we hit section 7, we'll dip back into the concept of a polygon. The nice thing about chapter 6 is the fact that it returns back to some middle school content that you've dealt with, unlike chapter 5. So you might feel like you're a little bit more at home with this chapter. Tomorrow you'll have to take care of your check for understanding for this lesson, as well as tomorrow you'll have to take care of your Math Excel, but I will enable your Math Excel to take care of tonight if you're feeling like you need to take care of it because you want to have tomorrow night off. We will be quizzing the Tuesday before Thanksgiving break, so please make plans accordingly if you are not going to be here for that day because your family is leaving early, so contact me as soon as possible. Today we're focusing in on sum of angle measures both inside and outside the polygon, so let's begin. The very first thing I need to start off with is the theorem 6.1, which is the polygon angle sum theorem. And what this theorem allows us to do is to find the sum of the measures of the interior angles of an n-gon. And when I say n-gon, that's just me saying the number of sides polygon, okay? So if I want to find a 3-gon, we all know that a 3-gon is really just a triangle. Well, to find the angle measures of the sum of the interior angle measures of a triangle, if I just want to use my n minus 2 times 180 formula, we would have 3 minus 2 times 180, okay? 3 minus 2 is 1. 1 times 180, that gets us 180. And as you and I have discussed, we actually already had the triangle angle sum theorem, but it's a really nice base case for this theorem because you can't have anything smaller than a 3-sided figure. All right, so here we go. First example problem. It says, what is the sum of the interior angle measures of a heptagon? All right, notice I have started to name my polygons. I do not have to have the number with a dash gone. So this is my reminder to you that you should know the names of the polygons. I'm going to say up to 12-sided figures. Hepta, if I look at that STEM word right there, hepta means 7. So what this really is a 7-gon or a 7-sided figure. And if I want to find the sum of the interior angle measures of a 7-sided figure, I'm going to use the formula n minus 2 times 180. So all I'm going to do is I'm going to plug 7 in for n. So we have 7 minus 2 times the quantity of 180. We follow order of operations and first work inside of our parentheses. So we have 7 minus 2, that gets us 5, and we have 5 times 180. And when I do 5 times 180, I get an answer of 900 degrees. So that is my answer. That is the sum of the interior angle measures for a heptagon. All right, my friends, it is now your turn. You have 2 got it questions, part A and part B. Let's check the answers in the work. So if you got the answers wrong on Edpuzzle, please make sure you are looking at these steps. So notice that we had answers of 2,700 as well as 13, okay? Something I would like to point out, notice that this came out as an integer answer. Had my answer come out as, for example, 13.3 repeating, okay? That would have showed me that I would have not had an integer number of sides, so this would be not possible, okay? So had I given you an angle measure that produced an n value that's not an integer, it's actually not a possible polygon, okay? That's just a little side note, a little fact for you to know in your little memory bank. All right, so let's return to the world of equilateral and equiangular. An equilateral polygon, as we all know, means all the sides are congruent to one another. Now, just because you're equilateral does not mean you're equiangular, as is evident in this diagram below. This figure is equilateral, and as you can kind of see, this angle right here is clearly not congruent to that angle right there. This is unlike equilateral triangles, which I'll talk about in just a second. An equiangular polygon is a polygon where all your angle measures are congruent. But once again, that doesn't mean that your sides have to be congruent, because this side and this side are clearly congruent by observation, but they're not congruent to these little pieces. Now, in a situation where you are both equilateral angular, then what we consider you to be is regular, okay? One of the most regular polygons we've dealt with to date is the equilateral triangle. And by one of our theorems in chapter 4, we learned that if we're equilateral for a triangle, then you are automatically equiangular, okay? I'm not going to show you this theorem under this slide here because rather than just giving it to you, I want to talk about why it's true in the next example, so we'll hop right back to it. The common housefly, Musca domestica, has eyes that consist of approximately 4,000 facets. Each facet is a regular hexagon. As you can see on my diagram here, hexagon is a six-sided figure. What is the measure of each interior angle in one hexagonal facet? All right, because I have been told that I am regular, that means that I know that all my sides are congruent, as well as the fact that all my angle measures are congruent to one another. So what I'm thinking about here is whatever the total amount of angle measure is for this diagram, aka the angle sum for this figure, it has to be evenly distributed from the angle measures because they would all be equivalent to x. They would all have the same value here. So we first need to figure out what the 6x's would add up to. So what the sum of their angle measures is. And to do that, I would use the formula n minus 2 times 180. All right, so I'm going to plug in 6. We have 6 minus 2 times 180. First, we work inside of our parentheses, so we have 6 minus 2 is 4. So we are left with 4 times 180, which tells us that we have a sum measure of 4 times 180, so, I'm having a blank here. 2 180s is 360, so 4 180s is going to be 720, okay? So that is what all the angle measures add up to. And as we discussed, we have 6 of those measures, and they're all equal, so I'm just going to divide this answer by 6 to find what my angle measures are each equal to. So when I do 720 divided by 6, I get 120. So therefore, x equals 120. Therefore, each of my angle measures is 120. Notice that I took the sum of the interior angle measures and I divided it by the number of sides. This is why this theorem that I covered up is true. If you have a regular polygon, to find the measure of each of the interior angles, all you're going to do is take the sum and you're going to divide it by n. So you're going to divide it by the number of sides of the polygon, okay? And this formula, like I said, you don't have to memorize. It just finds you the measure of each of the interior angles. All right, so now it is your turn. You're finding the measure of each interior angle in a regular nonagon. You got to know what a nonagon is. All right, so hopefully you recognize that a nonagon is a 9-sided figure. Therefore, the measure of each of those angles is 120 degrees, okay? Let's move on forward. What is the measure of angle y in the pentagon today? So we want to know this measure right here. And we've been given all these other measurements, 110, 120, 150, 90, and y. Well, I know that when I add up all these angle measures, it's going to add up to something. What that something is now something I can figure out. If I use the formula n minus 2 times 180, that'll tell us what all the angle measures are going to add up to. So I'm going to plug in 5 for my n because we are a pentagon. And so we're going to do 5 minus 2 is 3. And then we're going to do 3 times 180. And 3 times 180, that gets us 540. And so what this represents is the sum of all of the interior angle measures. And sum means I add. So I have 90 plus 110 plus 120 plus 150 plus y. And all of those interior angle measures add up to 540. So when I subtract all of these from 540, I am left with a y value of 70. So the measure of angle y is equal to 70. All right, here is your turn. You're finding the measure of angle G in the quadrilateral. And I'm sure many of you already know what the angle measures of a quadrilateral add up to. This isn't one you necessarily have to show a formula for. All right, so if you did not get the right answer on Edpuzzle, please check your work here. You should have an angle measure of 102. Here we go. We're almost done for the day. All right, so let's talk about exterior angles. So notice, remember, if you recall, exterior angles are a linear pair with their interior angles. So if I look at all these interiors, I have an exterior of 130. This interior gives me an exterior of 80. And this exterior is a 150. And when I added them all up, I got 360. Let's look at the quadrilateral. Same thing. Exteriors are going to be a linear pair with their respective interior angles. So we have an exterior of 71, an exterior of 115, an exterior of 75, and an exterior of 99. If I add those up, I get 360. I wonder if you can figure out what the theorem is that I'm about to give to you. Look at that. The sum of the measures of the exterior angles of a polygon at each vertex is going to be 360 no matter what size, okay? So when I add up all of the exterior angles, no matter the type of polygon, does not have to be regular. They're always going to add up to 360. That would be good always, sometimes never question. We always add up to 360 if we're adding the exterior angles. All right, so let's take care of this last example problem. It says, what is the measure of 1 in the regular octagon to the right? All right, so let's think of this logistically. We could find the measure of each of these interior angles. We've just discussed how to do that. That is definitely a possibility. And if I were to find that, I know that it's going to be a linear pair with 1. But let's think of this a little bit differently. We just learned a fact. Because all of the exterior angles add up to 360, I want to use this fact. Because all the interiors are the same, all the exteriors are also going to be the same. Because they are all congruent to the same supplement, that would be the congruent supplements theorem. So because they're all the same, I need to distribute them evenly amongst 360. So I'm going to do 360 divided by 8. Because all 8 exterior angles are going to be congruent to one another. So 360 divided by 8 gets me 45 degrees, and this would be equal to the measure of angle 1 in this regular octagon. Now notice this strategy only worked because I had a regular octagon, which meant that all my exterior angles were the same. Here's your last got it question. All right, once again, that strategy will work because you have a regular nonagon, and because all of the exterior angles are the same, that 360 has to be distributed evenly amongst the 9 angles, getting you a measure of 40. All right, well, I hope you look forward to our day tomorrow in class. Tomorrow in class, we will be practicing the content. And as I said before, if you're feeling super ambitious, feel free to take care of that 6-1 Math Excel today. Have a good day.